Okay, cool. Thanks. So this is about TinyStories, my project with Yuan Ju. So when we think about what it means to understand language or to be able to speak fluent English, the first things we usually think about are, to have some vocabulary and to have some grammatical abilities. And we usually think as facts and reasoning as things which are separate from actually being able to speak language. We think about facts as, Paris is the capital of France, Joe Biden is the president of the United States. You don't really have to know these facts in order to be able to speak fluent English, right? But I want to argue that you can't really separate those things because there are many, many facts that are really inherent into the understanding of language, and the same for reasoning. So let's look at these examples. Let's try to complete the first sentence. Jack was hungry, so he went looking for some. I would argue that any 2.5-year-old or most 2.5-year-olds can complete this sentence. Now, to complete it, you need to know some fact. You need to know that hunger plus desire equals food, right? That food is something that satisfies the desire, which is hunger, right? Now, let's look at the second example. Lily wanted to get either a cat or a dog. Her parents didn't let her get a dog, so instead she got a same story, right? Children can easily complete this. Now, to complete this, you really need to do some reasoning, right? You need to take the set cat plus dog, subtract dog from it to get cat, right? And one more ability that we kind of looked at, which we also think is very inherent to speaking a language, is contextual tracking. So let's look at this sentence. Ramona and Beezus walked up the street, met a girl in a red dress. The girl said to them, "Hi, I'm Jane. What are your names?" So, to complete this sentence, we probably want to say, I'm Ramona and this is Beezus, Ramona said. You need to keep track of, the characters, the cues, what's going on. You really need to produce a consistent completion. You need to follow the different entities and relationships between those entities that appear, right? Okay, so we have all these elements in language, but when we think about, large language models and the corpora they're trained on, well, they are very, very broad in the sense that, yes, they have facts, reasoning, vocabulary, grammar, but the number of facts is just vast. And not just facts, but, let's start with this. I literally pressed the random article button on Wikipedia twice. This is something I really like to do lately. Just look at a random article, hide the words with my finger, try to predict the next word, and try to think, what kind of abilities I'm using as I'm trying to do this. So, these two examples, the Q37 New York City bus, you need to know how to speak English to complete the next word here. But for most of the words, you also have to know a lot about, places in New York City, etc. And if we look, we can just paste this text into the playground of, GPT 3.5 and do the same with GPT-2 and look at the perplexities. The perplexity is more or less, how many guesses the model needs to do in order to predict the next word for, a typical word in the text. And what you see here is there is a vast difference. GPT 3.5 only needs like 4.5 guesses. So it has a pretty good clue what's going on. It already has learned the names of most places in New York City. Whereas GPT-2, it has no idea, right? It needs more than 20 guesses, meaning that, for most words here, it actually needs much more, so it can probably predict the word R in resorts, world, casino, are designed, but, it cannot predict the names of any of those places, right? On the other hand, let's look at this example of a simple story. It's a story about a boy named Timmy who loved to play with boats in the bathtub. He goes to the beach, he sees yachts. He can't go on the yacht, so he starts spinning, yada, yada, yada. Someone pushes him to the water. Timmy drowns. His dad is heartbroken and wished he'd never taken him there. Nice little story. Now let's, let GPT 3.5 and GPT-2 predict the next words here. So we see two things. First of all, the perplexities are both smaller, right? Like the previous slide was 4.5 and more than 20. Here it's 3.4 and 3.7. But they're not just smaller. Also, the perplexity of GPT 3.5 is much closer to the one of GPT-2. So this tells us that, GPT-2 has already kind of mastered this type of content. All the extra data and extra model size that goes to 3.5 is not helpful that much, right, in predicting the next word here. Now, so the internet is huge. It has a lot of facts in it, but it also has tons of patterns that those models learn. So, this is a few prompts I just tried a few minutes ago with GPT 3.5. What was the weather in Olympia, Washington during each day of the week of March 21st, 2014. Now, what you see here is mostly hallucinations. It hasn't memorized these things, but still it seems that what it outputs is very correlated with reality. So those models have learned lots of patterns, which are, some of them are kind of useful, but many of them are not so useful, right? And you can imagine how much of the capacity of those models, how many of the parameters are going towards, knowing which IP addresses belong to which, areas of the world, right? So, this kind of motivates us to try to design a data set that has all the elements of natural language, such as, grammar, vocabulary, facts, and reasoning. So in terms of depth, we want it to be kind of as deep as possible, but we don't want it to have this vastness, this breadth that you have on the internet with, so many facts, so many patterns, etc. Okay. So, our main idea was to just use the fact that kind of human development is, humans are born with a smaller brain, and at an early age, we're able to speak English, some of us, but, we don't know that many facts. But we can still, do some kind of reasoning, and, we have those core abilities already developing, but without those vast amounts of knowledge, right? So, we go to GPT 3.5 or GPT-4, and, we can now give it instructions. We ask it to write a story that only uses a 3 to 4 year old vocabulary. And, we can give it a structure, which we say, our data set is only short stories of, a few paragraphs. Now, if you do this prompt, you run into a problem. Even if you take temperature 1, many of the stories, like a huge proportion, will be about children going to the park, being scared of the slides. So, in a sense, the model is not super creative. The distribution you get does not really span all the knowledge of 3 to 4 year olds. So you have this problem of a data set with low diversity, and our way to address this problem is to just kind of find a way to inject randomness into the prompt. So we just prepared 3 lists of verbs, nouns, and adjectives, about 500 words in each, of words that 3 to 4 year olds typically understand. And we also prepared a list of elements that a story could have, like a story could have a dialogue in it, a bad ending, some kind of conflict, a twist in the plot, a moral value, etc. And now here's our prompt. So we basically generate 3 random words, and we ask GPT 3.5 or 4 to write a short story that somehow combines those words into the story, and perhaps also that the story has some subset of these elements that we randomly generated. So here's an example generation, write a short story, which only uses very simple words. The story should contain the verb decorate, the noun thunder, and the adjective ancient. Those were, randomly generated. It has the following features. It should contain at least 1 dialogue, and it has a bad ending. And I think this one was generated by GPT 3.5. It outputs this story. So the ancient is an ancient house. At some point, there is a girl living there. She wanted to decorate her room, so that's the decorate. At some point, a storm comes with thunder and everything. It gets louder and louder. Suddenly, the roof falls down on the pretty decorations, and they're ruined. That's the bad ending, I guess, for you. Okay, so we did this. We did about 500,000 calls in total and generated a data set that has about 500 million tokens, roughly half with 3.5 and half with GPT-4. And then, we got this data set and we trained some models on it. All of them were small models between 1 million and 35 million parameters. All of them with complete vanilla architecture based on GPT-Neo, there's no new ideas in the training whatsoever. Take the Hugging Face trainer, do the most straightforward thing. You do something between 5 to 20 epochs of training. 5 is usually already kind of almost saturates. And with these sizes, almost all the models can be trained on 1 node of 4v100s in less than 24 hours. Most of them only need 1 GPU, actually, not an entire node. And, let's look at a first example of what this gives. So let's take this story from the data set, first of all. So this is a story about Sarah and Ben playing in the snow. They make a snowman. At some point, some dog comes and, tries to destroy the snowman, and they say, go away, go away. The dog bites the scarf and the snowman's nose, blah, 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 Sarah and Ben. And then we take this part marked in the red brackets and we just cut it out of the story. We feed the beginning into a model and try to generate an alternative completion. So first of all, let's do this with GPT-2 XL that has 1.5 billion parameters. Let's see what it generates. So Sarah and Ben cry, look at the snowman in the snow. Ben asks to do something. Sarah tells him to go away. Her hand tightens on the little red button. Blah, 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 blah. He had saved the world. So I wouldn't say this completion is very consistent with how the story begins. In fact, if you look at this completion, you'll see that every sentence relates in a decent way to the sentence that comes before. But the only element from the story that actually remains throughout the generation is that there is some snowman there. Other than the snowman, nothing remains. Okay, it's just kind of a sentence by sentence generation. Okay, so this is GPT 2XL. Now let's do the same thing with our model that's almost 1,000 times smaller, so only 2.5 million parameters. Okay. So here Sarah and Ben are very sad and angry. They cry, they shout at the dog, bad dog, blah, blah, blah. At some point the dog starts being nicer, I guess. They say maybe we can make a new snowman for him. They hug the dog, give him a name. The dog wags his tail, everyone's happy in the end. By the way, if we look at the original beginning, you'll see that the original ending of the story, you'll see that it ends completely differently. Here they go home and their mother makes hot chocolate for them, and the dog is still bad, Now, so we took a story from the data set, we erased, and we generated a completion. This is already kind of an indication that, it didn't memorize the story. The ending is consistent, but it's different from what it saw on the training. Okay.
So just a quick clarification. So the prompt is all the text without being highlighted, right?
Yes.
Okay, cool. And then the highlighted is generated text.
Yeah. Cool. The highlighted is the generated text.
Thanks.
Yeah. Thanks for the question. Now here's another completion by another model, which is this time a bit bigger, so 22 million params, but it has only one transformer layer. So literally one self-attention, one MLP, embedding, output, that's it. Sarah and Ben are very sad. They cry and hug each other. They wish the dog would go away. Then they hear a voice. It's their mom. There is a mom in the original completion, but now the mom comes out of the house rather that they go into the house. I would say this completion is not perfect. If you read into the details, there are some inconsistencies, but it's still decent, right? And it's only one layer. So this story was in the data set. Now let's look at another story that's not in the data set. Arguably the models would do worse on it. So let's just look at one more comparison. Tom and Jane are friends. One day, Jane goes to Tom's house. He has a big pot of soup. She offers him the soup. He says, he offers her the soup. She says, yes, please, it looks yummy. Jane takes a spoonful of soup, but then she makes a face. The soup is, right? So GPT-2XL says, too old, Tom's cows, don't be that way. Your soup has to be fresh like your daughter. Okay, I'll stop here and continue to our model that has 28 million params. The soup is very bitter. She doesn't like it. She says, I don't like the soup. It's too bitter. Tom is sorry. He says, I'm sorry, Jane. I didn't know you don't like bitter soup. I'll make you something else. He makes her bread and cheese and everyone's happy. Okay. So kind of same story, GPT-2XL doesn't go very far in being consistent. Now, let's go back to the elements of language we talked about. Now we've trained the model on those stories. We never explicitly taught them any facts. But now we can try to use some prompts to infer whether, they learned some facts. So, I can just write it as if it's a part of a story. Alice was so tired when she got back home, so she went, GPT-2XL, if you look at the last column, says outside. So she went without the beginning. It makes sense to complete outside, I guess, if you didn't read the beginning of the sentence, right? But already our model that has 2.5 million parameters knows that the better completion is too bad. And when you go to 33 million, it's not just too bad, it's straight too bad. So it's already also picked up the sense of urgency in this sentence. She was so tired. Let's look at the second example, the cat plus dog minus dog equals cat. So the 2.5 million parameter model, instead she asked her mom if she could have a dog. That doesn't make sense. But really, actually, if you look at the sentence, the original prompt, the word dog appears twice in that sentence. So if you know next to nothing, and you just know that dogs and cats are nouns, and it could be either a dog or a cat, and you have like zero reasoning, then dog is kind of like the most plausible completion here, right? You need a little bit of reasoning, and our 33 million parameter model already says she asked her dad for a cat. The one layer model says she asked her mom again, which I guess is a valid completion. And GPT-2XL says she asked her dad. They brought her a Chihuahua, so that's a type of a dog, right? So it's a richer completion. It gives like the type of the dog, but it doesn't seem to have much reasoning. Last example for contextual tracking. Alice and Jack walked up the street, met a girl in a red dress. The girl said to them, "Hi, I'm Jane. What are your names?" So first of all, GPT-2XL, the last column, Jane said Jack and Kate. There is no Kate here, of course. Our 2.5 million parameter model doesn't do so well. Alice smiled and said, "My name is Daisy," but the 33 million model nails it. Okay. Yeah, so we just took a list of those prompts and tried them all and tried to see what happens as you increase the size of the model. And some things I find them pretty nice, because look at the first example. Can cows fly? Alice asked her mother. We looked at the data set and we tried to see if there's any point where it explicitly states that cows can't fly, and we couldn't find. Of course, it could be written in many ways, so we might have missed it, but we tried it with several different facts like this. And we already see at these sizes of models the magic that happens. You never explicitly stated this fact, but it has somehow magically inferred it from reading those stories and realizing that cows can fly, right? And you see that if you embed it into the conversation and the model is big enough, it actually knows that cows can't fly. And if you look at so what we did is I hear it's just the wrong answers are highlighted in red, the right ones are green, and whatever is kind of in the middle is yellow. And you see how the colors are changing from red to green as the size of the model increases. The last two columns are the one layer model and GPT-2XL, who are not doing super well on these prompts. We also have, so those are other examples of prompts that have some reasoning in them, and you kind of see the same pattern. It becomes greener as the model size increases. And somehow, when we get to 33 million parameters, it seems to almost always do better than the 1.5 billion GPT-XL. But of course, the prompts need to be aligned with our structure. It should look like a sentence in a story, and it should only use simple vocabulary. So those are reasoning prompts, and we have the same thing for contextual tracking prompts. So I won't go over those carefully. This is just to see, the pattern of colors. Now, one other thing we did is, okay, we trained those models. What's the best way to actually evaluate if they're good or not? And, usually the kind of benchmarks we have for language models are either you fine tune them on some downstream tasks and the downstream tasks have a single correct answer. And then you have, benchmarks like glue and all that. Or you can actually test them on generation, but then, it's very hard to. So there is the expected generation, but there are many ways to actually say the same thing. So those benchmarks are sometimes not that great, right? Because you cannot really match the strings. You usually do some kind of rouge score or something like that. So, what we thought is, now we have GPT-4. GPT-4 is almost like a human. What's better than just having a human check the story as if it's a teacher and the model is a student and say, did the model have, is it a good continuation? Are there grammatical mistakes? What's the level of creativity, consistency, etc.? So, what we do, our evaluation kind of paradigm is the following. We just have a bunch of beginnings of stories. We let the model complete them in some temperature on several different attempts. And then we basically give this to GPT-4 and we say, please provide your general assessment about the part written by the student. We pretend it's a human being that did this. We tell it where is the part that was completed. It's the part after the star, star, star. And we give it some, guidelines what to pay attention to. And for this completion, this is what GPT-4 says, the student's completion of the story is mostly consistent with the beginning. It maintains the focus on, the main characters, blah, blah, blah. The grammar is generally correct, but it does give some concrete comments, which I omitted here. But, it says it does not fully integrate the shiny decorations found in the attic. So it basically says there is a detail here that, the student didn't pay attention to. So, it seems to do a pretty good job. And then we ask it to actually give scores for grammar, creativity, and consistency. And, we did this for models of different sizes, and we did it also throughout the training process. And those are graphs showing how the different grades evolve. And you see first of all, they're pretty smooth. So you see that they are really increasing with training. You see that they're all pretty correlated with the validation loss. But actually, if you look at in a more nuanced way, you can actually see slight differences between them. So they actually give you a little more information than validation loss that we'll talk about in a couple of minutes. Now, here's a concrete example. We won't go over it due to lack of time, but you take the same beginning of story, you generate a completion with different model sizes, and then you let GPT-4 grade the completion. And if you look, at the right column, you'll see that the scores are basically increasing with the model size.
Interesting that the one layer has creativity much smaller.
Yeah, but there's, this example, there's also randomness here. So it does have smaller creativity, but not that much. The effect is not that strong. And, here's a table showing how the grades depend on both, the hidden dimension of the model and the number of layers. And by, looking at this table, which, we won't really eyeball it together, but I do want to give you some interesting patterns that you can observe from it. So it looks like the depth of the model is more crucial for consistency than for grammar. So that kind of makes sense because grammar is more superficial. It's kind of more local. You only need to know the sentence you're looking at, and it's also kind of easy to master it. Whereas consistency, you really need to remember that in the beginning of the story, there were the decorations she found in the attic. You kind of need more global, interactions between the tokens to get that right. We can also see that our small, okay, so grammar, it reaches a plateau basically first. So it's kind of the easiest to master. Consistency comes next, and creativity comes last. This is both in terms of model size and the number of training steps. Now, our models, like our small models, they reach almost perfect scores in terms of both grammar and consistency, but creativity, there is still a way to go between our models and GPT-4. So it really suggests that kind of creativity is the hardest, score to master. And we also see some kind of emergence here. So for 1 million parameter models, they basically never produce a consistent completion. And at 3 million, it doesn't always happen, but it already happens, not very rarely. Okay, so one more thing we did is we built another data set, which is an instruction following version. So we don't just have the stories in this data set, but we have the story preceded by a set of instructions that you need to follow in order to create the story. So this, I'll just show you one example. Here the model needs to create a story with a given summary. The summary is, 2 kids build a sand castle, blah, blah, blah. The story needs to have the features, it should have a dialogue, it should have a foreshadowing element and a plot twist. It should contain a specific sentence. One day she went to the park and saw a beautiful butterfly. And it should also contain those 3 words. So we trained models on this, and then, we can try to see if they can actually follow instructions. A nicer thing we can try with this is to test if there is some kind of out of distribution generalization. So we saw several types of instructions, such as, which words are in the story and what is the summary of the story. What we did is we trained models where you never combine 2 specific types, namely words and summary. So the models were never trained on combining specific words and also on training to a summary. But in test time, we tried, specifying both words and summary. And this is one example that basically, I think it does a pretty good job. So this is a 25 million params model. You give it, this particular summary, and it follows it, and it also combines those 3 different words, which, are not obviously there, like if you just have the summary. Okay. Next, so what we try to test, since we have smaller models, hopefully maybe those models are more interpretable in terms of, you can actually see what the neural network is doing, what each component is doing. So we tried both, we tested both what happens with the neurons in the MLP and what happens with the attention heads. So what we see here is the following thing. So for every neuron, which is just, a coordinate in the intermediate layer of the MLP, we look which tokens activated the most. So we just fed it a story, we just took 20 stories from the validation set. We fed it the story, and we checked which tokens induce the highest value to this particular neuron, the highest activation. And we marked those tokens in red. And we tried that for several different neurons. So what you see here, we picked layer 7, which is one layer before last. That's kind of a random choice, but it makes sense to pick a layer that's like already quite deep, because maybe there was already some computation done before this layer. And we took the first and second neuron. Everything is permutation invariant in this layer. So we could just take any other two neurons, just as well. So those two neurons are not cherry picked. They're just two typical neurons. And, we just, so the words you see in red are just the highlighted tokens. And I guess you'll agree with me that in the first one, we, I, and all of them are in the beginning of some quotation. So they all have kind of a common role. For the second neuron, push, ran, pushed and pulled, come, pushed. Okay, I guess all of these are kind of actions in the sentence. And I mean, maybe they have some extra similarity in addition, I'm not sure. And then we looked also at the particular neuron that has the highest activations in total from all of the neurons. That turned out to be the 54th neuron. And I think it's pretty nice. What we saw is that this neuron, it basically fires on the first time that the main character of the story is introduced, which makes a lot of sense. You will have something like that, because many times in your completion of the next word, okay, now should be probably the main character, right? So it makes a lot of sense. The token will have that embedding will have this information, right? So this is for our model that only has, 64 dimensions in the hidden, like in the embedding dimension. On the other hand, if we do the same thing for GPT-2, these are just, two typical neurons we took. Doesn't seem to have any particular role. So, the first neuron highlights on the word to, but also keep, grumpy, quiet. So, some of them are adjectives, some adverbs. To, I'm not sure even what it's called in English. They're all, also the second one. Okay, so it does suggest that as you make the models smaller, they become more interpretable. We did the same thing for attention heads for the one layer model that we have. So what we observe is that the attention heads, there's a dichotomy. Some of them are completely local. So they just, attend to tokens that are close by. So those are the attention patterns. You see they're all close to the diagonal. So we just distance-based attention. And some of them seem to be just semantic. So, in this example where, two kids lost a banana and they go to the park to look for it, you really see that one of the heads, the words the and all attend to the word banana, which is, kind of like the main entities in the story. Another head, they all attend to park, and another head attends exactly to the tokens representing the characters. So, seems pretty interpretable, at least to some extent. We also tried, at least we did some preliminary experiments, trying to use this for neural architecture search. So we know the scaling laws, there's two main papers, one by OpenAI about scaling laws and other the Chinchilla paper by Google. which both find that as you increase the number of flops, the compute in the training, there is some optimal balance between model size and number of tokens to use. The total number of flops is just the product of both of them. And the question is, where is the optimum? How should I balance between model size and, number of steps in the training? And both of these papers find that there is some polynomial law that if you try to optimize, the model size should depend polynomially on the number of flops in the optimum point. And the two papers they both find polynomial laws, only different ones. So the exponent is different. And, we did the same thing. It only took us like a few days on preemptible nodes in the cluster. And we got, all these data points, which, we got many, many more. These are just the ones close to the optimum. And you see that as the model size increases, the number of flops that this model size is optimal for, you take the log of both, it looks, arguably more or less linear. So already at those scales, you see the same phenomenon, which suggests that indeed maybe there is some universality going on here. Okay, so just to wrap up some, future directions from this project. So many of the findings we saw are pretty preliminary. There's much more work to do in, for example, in neural architecture search, in interpretability, etc. I think the biggest question is, so it's very easy to get insights on this data set in terms of compute. You have an idea, you can test it in one day. But are those insights actually relevant for, LLMs? I think this is the biggest question. Is there any reason to think what's happening here will be true at large scales? Suppose we find some architecture that's, doing really well here. Can we translate it? Maybe we should want to think about a hierarchy of data sets, and could this be used for curriculum training? And last question, which is already partially answered in a follow-up work, the Phi-1 paper, now available on arXiv, is, can synthetically created data sets actually give rise to better LLMs? Okay, thanks. I'll finish here.